In this video, I'm going to take you through how to do multi-step calculations. The most important thing is to make sure that you know the equations. So I've chosen 7 questions which could come up on the paper 1. So here are the equations for paper 1. I'm going to go through them once and then use them continuously as I go through the questions. So first we have the energy equations. Kinetic energy is a half times the mass times the speed squared. We've got gravitational potential energy is mass times gravitational field strength times height. We've got elastic potential energy, which is stored in springs and elastic materials, which is 0.5 times the spring constant times the extension squared. We've also got work done, which is an energy transfer in joules, is equal to the force applied times the distance moved by that force. We've got thermal energy, when you're heating something, is equal to the mass of the substance times the specific heat capacity of the substance times the temperature rise. Delta means change in the temperature. We've got thermal energy needed to melt something or boil something at constant temperature is equal to the mass of that substance times the latent heat of either fusion, if you're melting something, or vaporization, if you're boiling something. And from the particles topic, we have density is mass divided by volume. We've also got this from the energy topic. Efficiency is useful energy out divided by total energy in, or useful power out divided by total power in. The next equation is probably the most important equation of everything. Energy is power times time. Remember, when you see power in watts, that is joules per second. That's the rate at which energy is transferred. These are electrical equations. So we've got the energy transferred, electrical energy transferred is equal to the charge flowed in coulombs times the potential difference in volts. We've got power is equal to voltage times current. There's another equation which allows us to work out electrical power, and that's current squared times resistance, I squared R. We've also got the total charge that flows around a circuit is equal to the current times the time. And finally, potential difference in volts is equal to current times resistance. Now you need to just write these out loads and loads of times and say to yourself what each symbol means as you're writing them out, so that gets into your longer term memory. Once you know these equations thoroughly, you can start accessing multiple step calculations with ease. But these are techniques that you now need to go through. The first thing in multi-step calculations is I always think about this. Energy is power times time. And the other thing you need to think about is prefixes. Because in higher papers, they're going to use this about 80% of the time in multi-step calculations. Energy is power times time. And also they'll be testing your prefixes. So always put that down to start with as a reminder. So now you need to go through the question, highlight what you know in symbols and also what you need to calculate. So the question says calculate the time. So I'm going to put above there T equals question mark. It would take a 2.4 kilowatt kettle. So watts is power. So I've been told the power. Remember that's in kilowatts, which is 1,000. So that's 2,400 watts. A kettle to heat 700 grams of water. So that's the mass of water, which must be in kilograms. So that's going to be 0.7 kilograms from 20 degrees to 100 degrees. So my change in temperature is going to be 80 degrees C. And I'm told the specific capacity of water is 4,200. So I know C is 4,200 joules. So next I need to do is to identify an equation which has time in and something else. And of course, I'm alerted straight away to energy is power times time. So first thing I'm going to do is to write that equation out. Energy is power times time. I'm then going to rearrange it because I want to work out time. You can use a triangle, but what I'm going to do is time is energy divided by power. You could use a triangle if you want to. Then I'm going to put what I know in. So, do I know the energy? No, I don't. Do I know the power? Yes, I do. 2,400 watts. So I'm now going to highlight this because that's something I don't know. But I should be able to work it out from what else I've been given. So I'm looking for an equation that links energy with mass, temperature rise, and specific capacity. Of course, that is energy equals mass times specific heat capacity times the temperature rise. So now I'm going to put my values in. I've got 0.7 times 4,200 times 80, and that gives me that many joules. I can now put that into my equation here. So I've got the energy in joules divided by the power, and that gives me 98 seconds. And that is the answer. So the second question, a copper block is heated by a heater of power 77 watts. So again, I'm going to highlight what I know with symbols. For 5 minutes. So that's time, and of course time has always been seconds, so 5 times 60 is 300 seconds. The temperature of the block changes from 20 degrees to 40 degrees, so my change in temperature is 20 degrees C. Calculate the mass of the block, so mass equals question mark, m equals question mark, and I'm told the specific heat capacity of the copper is that, so specific capacity is 385. So what I'm now going to do first of all is I need to work out mass. So what equation links mass and these? Well, of course it is this equation here, energy equals mass times specific heat capacity times by the temperature rise. Now I need to work out the mass, so I'm going to follow it and I'm going to rearrange the equation first for mass. So I'm going to put, so mass is equal to energy divided by specific heat capacity times the temperature rise. You again can use a triangle if you need to. I'm then going to carry on by putting in the things I know. So do I know the energy? The answer is no. So I'm going to leave that blank. But I do know the specific heat capacity, and I do know the temperature rise of 20 degrees. So what I need to do is work out the energy. So there must be something here where I can work out the energy. And again, remember the key equation, energy is power times time. So I'm going to somewhere else write energy is power times time. And of course the power is 77 watts, the time is 300 seconds, and that gives me 23,100 joules. Now I can put that into the equation here, and I can now work out my answer, and I get 3 kilograms. Don't forget, when you're doing this on a calculator, it's really important to bracket the bottom section. If you don't bracket the bottom section, you end up doing 32,100 divided by 385, and you end up timesing by 20, so make sure you put the brackets in. So the third question, it says 2,300 coulombs of charge. So charge is given the symbol Q. So I'm going to write Q equals 2300 coulombs of charge flows through a kettle's heating element when it takes 3 minutes 20 seconds to boil water. So I've got to change that into seconds. So 3 minutes is 180 seconds plus 20 is 200 seconds. Calculate the potential difference. Well, that is V, voltage. Potential difference across the heating element if the resistance is 20 ohms. So the first thing I need to do is think about an equation which links voltage and one of these. And so I'm going to start with V equals IR. Now it might not be right, but we just have to keep working through and see. So I want to work out voltage, which is current times resistance. I don't know the current, but I do know the resistance of 20 ohms. So the first thing I want to do is think, have I got something which links current I, Q and T? And of course we have Q equals IT. So Q equals I times T. So I is equal to Q divided by T, which is equal to 2,300 divided by 200, which gives us 11.5 amps. I can now put that back into the equation here, and 11.5 times 20 gives me 230 volts, and that's an easy 4 to 5 marks. So by now you should be getting the hang of what to do. So it says a catapult with a spring constant of 8.5 newtons per meter. So spring constant is given the symbol K. Is stretched by 30 centimeters. So that's the extension, and of course centimeters must be converted into meters, so extension is 0.3 meters dividing by 100. To launch a 50-gram ball vertically upwards. So I've got a mass equal to, and that's in grams, I've got to divide by 1,000, which gives me 0.05 kilograms. So I've got a catapult with a spring constant of 8.5 newtons per meter, is stretched by 30 centimeters to launch a 50-gram ball vertically upwards. And I'm told the gravitational field strength is 10 newtons per kilogram, and that is G is 10. So it says calculate the maximum height the ball could reach. Quote your answer to 2 significant figures. So what I always do is when you've got the answer to quote, which might be somewhere down here where it says the answer, underneath you need to write 2SF to remind yourself when you write the answer in your exam paper that that's what you've got to do it to, because you're bound to forget by the time you've finished. So it says calculate the maximum height, so H equals question mark. So I've got to think of an equation that links height and some of these. I can think straight away it's mass, gravity and height, which is gravitational potential energy. So that's what I'm going to start with. Gravitational potential energy is mass times gravity times height. Even if I haven't really understood the question, I can still put this down and rearrange and then move from there. So I need to work out height. So I'm going to rearrange the equation. So height is equal to gravitational potential energy divided by mass times gravity, and I put that in brackets to remind me to do that on the calculator. Now I'm going to put in what I know. Do I know gravitational potential energy? No. Do I know mass? Yes, 0.05. And do I know gravitational field strength? Yep, I've been given it as 10 in this question. It sometimes is given as 9.8 as well. So what I need to do is find an equation which allows me to work out energy, because this is an energy change. And of course the energy stored in the spring is going to be elastic potential energy, and that is converted into gravitational potential as the ball is fired upwards. So even if you don't understand that, you need to think, right, what equation do I have for energy? What have I still not used? And of course energy for elastic potential energy is 0.5 times the spring constant times extension squared. So that's going to be 0.5 times 8.5 times 0.3 squared. Really important you write the equation down first, because the amount of people that forget to square that. And that gives us 0.3825 joules. So that elastic potential energy was converted into gravitational potential energy, which I can now put in here. And that divided by mass times gravity in brackets gives us 0.765 meters. Now I've been asked to quote it to 2 significant figures, so in my answer I'm going to write 0.77 meters, and that will give me my extra mark for 2 significant figures. Finally, it says, why in reality would the height reached be less than this? Well, because some of that elastic potential energy will be converted into thermal energy as the ball rises up, rather than transferred into gravitational potential. So the next question says, an electrical blanket used in bed for 7 hours transfers 5.04 megajoules of electrical energy. Now remember, I forgot earlier to remind you to first of all write down energy is power times time, and to write down prefixes as a reminder when you're doing a multi-step calculation. You might not need it, but quite often you do. So an electrical blanket is used for 7 hours. Well, 7 hours, that's the time, and that is 7 times 60 times 60 for number of seconds in a minute, a number of minutes in an hour, and that gives you 25,200 seconds. Transfers 5.04 megajoules of electrical energy. So this is energy, E equals, and of course it's mega, which is a million, so that's times 10 to the 6. So 5.04 times 10 to the 6 joules. You could just multiply by a million. Calculate the current flowing, so that's a symbol for current, through the blanket's heating element with a resistance of 4 ohms. So R is 4 ohms. Now again, even if you don't understand what the question actually means, you can still work out the answer, because I've got to find an equation that links I and R, or any of the others. And the first one I'm going to write is, I'm going to try V equals I times R, which is that equation there. I want to find I, so I'm going to rearrange. So I equals V over R. I'm then going to put the values in I know. Do I know the voltage, the potential difference? No. So I'll leave that blank. Do I know the resistance? Yes, 4 ohms. So now I'm going to see if I can find a link between voltage and what I've got left, which is energy and time. And of course, I don't actually know an equation which links voltage, energy and time. And in multi-step calculations, you won't be asked to do 3 different calculations. So I can't use that equation. So I'm going to try a different one. So what else do I know that links current and one of these? Well, the other one is, of course, power is current squared times resistance. So I'm going to try that one instead. So power is current squared times resistance. So I want to work out current. So I squared is power divided by resistance. I don't know the power, but I do know the resistance is 4. And of course this time I now can work out the power because I'm given energy and time. So we've got energy is power times time. So power is energy divided by time, and that was 5.04 mega electron volts, which is mega electron joules, which is a million joules, divided by the time, which was 25,200 seconds, and that gives us a power of 200 watts. So now I can put that power into here, and that gives me 50. Now be really careful. Luckily you wrote the equation out. We wrote the equation out, so it's I squared is 50. So I will equal the square root of 50, which is equal to 7.07. But I was told to quote the answer to 2 significant figures, so my final answer will be equal to 7.1 amps. So we've got 3 more questions to go. These ones are getting slightly more tricky as we go through on purpose to really build up your resilience to answering these questions. So it says an electrical cup heater plugged into 24 volts, So I know the potential difference is 24 volts, carries a current of 10 amps, so I equals 10 amps, is used to heat 250 grams of water. So that is the mass, and that's got to be in kilograms, so divide by 1000 is 0.25 kilograms of water at 20 degrees C. The heater is on for 4 minutes, so my time is 4 minutes, so that's 4 60s are 240 seconds. Calculate the final temperature of the water. So I need to know the final temperature of the water, and specific heat capacity of water is 4,200. So C is 4,200 joules. Well, the first thing is I need to think what's happening. This is going to heat water from 20 degrees up to a final temperature. So I first need to work out the change in temperature so I can work out the final temperature. And therefore, what equation links temperature or change in temperature with things here? And of course it is energy is mass times specific capacity times the temperature rise. So I'm going to start with that equation, even if I don't know how I'm going to finish it off. Mass times specific capacity times the temperature rise. What I'm now going to do is rearrange again for what I need to calculate, which is the change in temperature to start with. And that's going to be equal to the thermal energy supplied divided by the mass times the specific heat capacity. So now I'm going to put in what I know. Do I know the energy? No. Do I know the mass? Yes, it's 0.25 kilograms, and specific heat capacity was 4,200 joules. So I'm going to use my confidence that somehow I'm going to be able to work out the energy knowing this. And of course, the classic is knowing, again, are they testing me with this? Energy is power times time. So, do I know the time? Yes, I do. It is 240 seconds. Do I know the power? Well, it doesn't look like I know the power, but what else have I been given? Well, I've been given voltage times current. So power is voltage times current. So power is voltage times current, which is equal to 24 times 10, which is equal to 240 watts. I can now put that into my equation here. So we've got 240 times by 240, and that is equal to 57,600 joules. I can now put that back into this equation here, and that gives me energy divided by mass times specific heat capacity, and that gives me a final value of temperature rise of 55 degrees C. Of course, we weren't asked for the temperature rise, we were asked for the final temperature, and of course the initial temperature was 20. So the final temperature will be equal to the initial temperature plus the temperature rise, which is 75 degrees C. So that looks a much more tricky calculation, but if you follow the steps by quoting the equation you need, rearranging it, putting the things in you do know, and then solving it for the things you don't know, you can answer that question, which is a good 6 marks in your exam. Second from last question, what I've tried to do this time is show you how we might have to use the density equation from particles in energy equations. So it says the volume of 2.5 times 10 to the minus 4 meters cubed of water from a shower condenses on the mirror. So first thing I'm going to do is to write V for volume is 2.5 times 10 to the minus 4 meters cubed. Calculate the energy released in kilojoules when the condensation forms. If the density of water is 1000 kilograms per meter cubed, so density is 1000, and specific latent heat of vaporization, so that's given the symbol L, is is 2.26 times 10 to the 6. Now, I've been asked to give my answer in kilojoules, so where you have the answer written in terms of your answer sheet, there'll be a line, and I'm going to write underneath kilojoules just to remind me to quote it in kilojoules, else I'll lose my marks. I'll lose a mark. So I'm going to go back and now have a look and see what equation I need. So it says calculate the energy released. So E is question mark. So first of all, I'm given latent heat. So I know the equation I must have to use is energy is mass times latent heat. So I'm going to start by quoting that equation. I'm going to rearrange it. Actually, I don't need to rearrange it because that's what I need to work out. So I'm going to put what I know in. Do I know the mass? No. Do I know the latent heat? Yes. So I've got to work out the mass. So looking back, what links mass with volume and density? Well, of course, it is density is mass divided by volume. So I've got to rearrange that. You can rearrange that in a triangle, or you can do it in your head, but I'm going to just use a triangle for you. So density is mass divided by volume. So mass is going to be density times volume. Take that to the other side. So we've got mass is density times volume, which is 1,000 times 2.5 times 10 to the minus 4. And if you're not sure how to do that on your calculator, let me just show you now. So what you need to do is do 1,000, then times by 2.5, and then you need the times 10 to the x, or exp it's sometimes called. So press that. You now need to put a negative in. Don't touch that sign there, that means minus. You need to do the negative up here, so minus 4. And that will give me a quarter, 0.25. So that's 0.25 kilograms. Now I know the mass, I can put it into the equation over here. And then 0.25 times 2.26 times 10 to the 6. And again, I'll just remind you how to do that. So 0.25 times 2.26, and again times 10 to the 6, so times 10 to the 6 gives us 565,000 joules. And I was asked to quote it in kilojoules. So I'm going to divide by 1,000, so my answer is 565 kilojoules. Always important to write down extra things you meant to answer it in underneath where you're going to record the answer, so it reminds you. So the final question I've written is one that contains both specific heat capacity and latent heat. And this is the type of question that was written once 2 years ago in a higher paper. So I'm just going to remind you that when we heat a substance, if we're thinking about the energy we put in and the temperature rise, remember first of all, when you heat a substance, you're going to raise its kinetic energy as its temperature rises. But then when it gets to melting point or boiling point, the temperature stays the same. And so we've got two equations to work out the thermal energy we're putting in. One is where the temperature is rising, we use thermal energy is mass times specific capacity times temperature rise. When the thermal energy is when the temperature is staying the same because of a change of state, either solid to liquid or liquid to gas, we use energy is mass times latent heat. So that's going to help us with this question. And again, I'm going to remind myself that energy is power times time, and remind myself to think about prefixes. So it says a 3 kilowatt kettle. So we know watts is power. So I've been told the power is 3 kilowatts. So that's 3,000 watts. A 3,000 watt kettle's automatic switch off is faulty and does not switch off. The kettle is left on for 10 minutes. So I've got a time equal to 600 seconds. before the owner realised the room is full of steam and switched it off. The mass of the water in the kettle at the start was 800 grams. So I know the mass at the start is 800 grams. And its initial temperature is 220 degrees. So initial temperature is 20 degrees. Calculate the mass of water that boiled away. Now this is a much more complex question, and unless you understand what it's asking you, you will not be able to access it. So we're putting a certain amount of energy in, and the energy we're putting in is the power times the time. So I'm going to first work that out first. The energy that we put in to this water is power times time, which is 3,000 times 600, and that gives us a massive 1,800,000 joules. So what's that energy doing? Well, first of all, that energy is going to raise the temperature of the cold water in the kettle of mass 80 grams from 20 degrees up to 100 degrees. And when it boils, the rest of the energy is going to be used to vaporize a certain mass of water. And that's the mass that we need to calculate, the mass of water that is boiled off. So I'm going to first write this. The energy supplied will do two things. It will heat water to 100 degrees C, plus it will vaporize water at 100 degrees C. So now let's put the equations in. The energy supplied was 1,800,000 joules. It first of all heated water. Well, that's going to be this equation here, because we're raising the temperature from 20 degrees to 100 degrees C. So it's going to be the mass, which is 800 grams, which I should have converted then, but I didn't, into 0.8 kilograms. So we've got 0.8 times by the specific heat capacity of water, which is 4,200, times by the temperature rise, which is from 20 to 100, which is 80 degrees. And that will give me the total energy that I've used out of that amount to heat the water up to 100. The rest of that energy, before the kettle is switched off, will be used to vaporize the water. And so the mass of water that I'll be able to vaporize and boil away will be equal to the mass, which I don't know, times the latent heat, which I do. And be careful, the latent heat is given in kilojoules. So that's 2260000 times by 1,000 joules. I'm then going to simplify this. That gives me that many joules plus 2260000 times m. So what I'm now going to do is I need to make m the substitute of the equation. So I'm first going to take this amount over to the other side. It's adding on this side, so I'm going to take it away. So we've got 1,800,000 minus 268,800 is equal to so therefore this together is equal to 1531200, and that equals that much times by the mass. So now I've got to divide by 2,260,000. So the mass is going to equal that amount divided by 226,000, and that gives 0.678 kilograms. So a really tricky question, but it's remembering what's happening to the water, and that will be the highest level question you could possibly get, which links specific heat capacity and latent heat in one question by raising something's temperature and then either melting it or boiling it.